Now we're in part 2 of our mini-series on Abel and Jacobi's approach to elliptic integrals. In this part, we're going to discuss Abel and Jacobi's main innovation, namely inversion. Recall that in part 1, we said that elliptic integrals come from computation of arc lengths of curves. For example, in the case of the Leibniz gate curve that we did in part 1, the length of the arc connecting the origin to the point corresponding to r equals to a is going to be given by this integral. Now, the reason why mathematicians were so intrigued by this integral is because they cannot be expressed in terms of elementary functions. Thus, they define a new transcendental function. This functional viewpoint was first taken by Legendre. He used this approach to study these elliptic integrals for a long time, thinking of them as transcendental functions of this upper limit. Then, in his later years, suddenly two younger mathematicians came on the scene and bring about a completely new approach. Both of them came up independently with the idea of inversion. It turns out that the right object to study are the inverses of these elliptic integrals, which we nowadays call elliptic functions. Instead of viewing u as a function of a, like Legendre did, Abel and Jacobi view a as a function of u. To see where this comes from, let's look at the computation of arc length on the unit circle. Recall that in radian, the arc length bounded by an angle is just going to be equal to the product of the radius with the angle. So on the unit circle, we should have that the arc length element is going to be equal to d theta. This means that this arc length can be given by integral from 0 to alpha of d theta. Observe that this integral is actually equal to alpha. That is because the length of the arc that bound the angle alpha must be alpha, or alternatively, you can just integrate this. Now, let's change variable. Instead of using this angle, we're gonna use the y-coordinate. Differentiating this expression allows us to rewrite d theta in terms of just y. Now, plugging this expression into the integral here gives us the following integral. Now, question, what is this upper integration limit? Well, that should be the y-coordinate of this alpha, right? And what is the y-coordinate of this alpha? That is just sine alpha. Thus, from this discussion, we see that for this integral here, the inverse is just the sine function. Because look, the inverse here, this a, is just sine of alpha, and alpha is equal to u. More generally, we can view trig functions as inverses of these arc length integral, and so we can now think of the inverses of these elliptic integrals as generalization of trig functions. We call these functions elliptic functions. Unlike Legendre, who focused on elliptic integrals, Jacobi and Abel focus on elliptic functions. Since these elliptic functions are generalization of trig functions, we would expect them to have some similar properties to trig functions. For example, there should be some kind of addition theorem, generalizing the addition law for trig functions. And then there should be some kind of periodicity. In the next video, we're gonna see how Abel proved the addition theorems and double periodicity of these elliptic functions. Actually, he proved this for specific elliptic functions called, aptly so, Abel elliptic functions.